Well, thanks so much, Dan, for that really nice introduction. And thanks so much, everyone, for having me. I really appreciate the opportunity to speak with you. So I've still actually never physically been to the CCA, despite being in the vicinity for quite a while now. So hopefully someday I can visit when things are safe again. So I am really motivated by trying to understand the demographics and the diversity of extrasolar planetary systems. So what kind of systems exist in our galaxy and how do they differ from our solar system and why? And so to investigate this, as Dan said, I primarily use orbital dynamics and theory to study the observational patterns that we see in the data. And in this talk, I'm going to focus on the influential role of tidal dynamics for short period planets. And within this, I'm going to highlight the surprising and kind of unexpected role of the planetary obliquity or axial tilt. And I just want to mention right off the bat that these planetary obliquities are not generally detectable for exoplanets yet, but there are some methods that are promising for the future for direct detection, which I'll mention towards the end of the talk. So I think that still kind of one of the most remarkable discoveries in the field of exoplanets thus far is the realization that roughly half of sun-like stars are accompanied by close-in small planets with orbital periods ranging from days to months. And I'm really interested in this population of close-in planets, both because they represent such a large fraction of extrasolar systems, but also because they help enable some of the really most exquisite orbital and physical characterization. So this is just a graphical representation of systems discovered by the Kepler mission, where the radial coordinate is the logarithmic semi-major axis. And you can see that this population of planets contrasts really sharply with the solar system, where the inner edge is marked by Mercury's 88-day orbital period. And these close-in planets are often kind of in between the sizes of Earth and Neptune, as you can see with their size scales. And a large fraction of them are in multi-transiting systems, as you can see in this kind of upper right here. And I'm primarily going to be focusing on these multi-planet transiting systems today. So these systems of multiple transiting planets exhibit a lot of really interesting structure and regularity. So one of the kind of quintessential examples of such systems is Kepler-11, which hosts at least 6 planets, and it was discovered back in 2011. So this system is really compact, circular, and flat. So the planets are all kind of somewhere in the super-Earth to sub-Neptune regime. They're all orbiting inside Venus's orbit, and at least the inner 5 have pretty uniform orbital spacing. So the system is pretty structured in the sense that it has really low complexity. It's almost kind of as architecturally simple as a planetary system can get. And if we look at these same features on the scale of the whole Kepler multi-planet population, we see that this orbital structure continues. So systems as a whole tend to have pretty low eccentricities and inclinations, as we can see in this sort of heat map of the average eccentricities and inclinations that occupy this kind of fairly low bottom left regime. In addition, the distribution of orbital spacings between planets in these multi-planet systems peaks at around 20 mutual Hill radii, and they tend to have fairly uniform spacings within a given system. So this is, again, kind of signaling the preponderance of these really highly structured, evenly spaced, not very complex systems. This structure actually continues beyond the orbits, though, into the physical properties of the planets. That is, planets in the same system tend to have fairly similar masses and radii. And this intrasystem uniformity, or kind of peas in a pod, as you could call it, was first pointed out by Weiss et al. In 2018, and then our paper from 2017. So this is easy to see with the radii on the right, that if you kind of scan your eyes down through various Kepler systems, you can see that the radii in a given system tend to be much more similar to their neighbors than they would be if you were to just pull these randomly from the population. And this depiction, you can also see the uniform orbital spacing pretty well as well. On the left, we can see this intersystem uniformity for both the masses and the radii, where all planets in a given system have the same color and are connected by lines. So you can again see that they're much closer to one another on this mass radius plane than they would be if they were just assembled randomly from the population. And if we measure the dispersion of planets on this within a given system on this mass radius plane, and compare that to what we would get if we were to just assemble systems randomly, we see that the real systems are much more clustered on this diagram than they would be if there was no mass radius uniformity. So far, it kind of looks like everything's kind of straightforward in a sense, like these systems appear really structured in both their orbital and physical properties. But it's not quite that simple. If we take a closer look, we can contrast some of this first order structure in their orbits and physical properties with some second order, what I'm calling architectural anomalies. And I don't really like that phrase, but I couldn't really think of a better way to say it. And what I mean by architectures is sort of the arrangement of planets in their orbits and their physical properties. And by anomalies, I'm talking about kind of complex deviations from the uniform structure. And there are many examples of this, but I just want to point out a few here. So one example is the bimodal nature of the radius occurrence rate distribution, where this kind of lower peak has come to be known as the super Earths, and the upper peak have been now are known as the sub-Neptunes. Another dichotomy that we see is in the eccentricity distribution of close-in planets, where multi-transiting systems tend to have much lower eccentricities than single transiting systems. So here's another kind of example of a second order dichotomy. Another architectural anomaly is if we look at the period ratios of adjacent planets in multi-planet systems and take a histogram over all of those different period ratios, we see that this distribution is kind of smooth overall, but that there's these interesting pileups just wide of a 3:2 and 2:1 period ratio, and these are called the first order mean motion resonances. And finally, another example of a architectural anomaly there's this subset of systems with extremely close-in kind of outlier planets that are sort of separated off from the inner edge of an otherwise fairly uniformly spaced system. So I'm going to talk about a few of these today, specifically these bottom two architectural anomaly examples, but all of these features of these close-in planets require explanations, and if we can figure these out, we can better understand planet formation and evolution of these close-in planets. So I would kind of argue that many, but not all of these architectural anomalies likely arise from post-formation dynamics. So by that, I mean kind of evolution of the planetary system after their initial formation in the protoplanetary disk. And such post-formation dynamics includes things like resonance interactions between planets, planet-planet scattering, which is a gravitational effect, tidal interactions due to tides that the stars raise on their planets, radiation-driven effects, so effects due to just having such strong stellar radiation, giant impacts, etc. So a wide range of things happening after the system's formation. And in this talk, I'm going to be focusing on the role of tidal interactions in sculpting the architectures of short period planets. So tidal interactions are particularly important for short period planets because they have a really steep inverse distance dependence. So the magnitude of the tidal force goes as 1 over distance cubed. And so it leads to a fairly significant tidal distortion that it's like kind of exaggerating here, but you kind of get what I mean. This tidal distortion in the direction of the host star. And whenever this tidal bulge is forced to shift due to either orbital motion or rotational motion of the planet, then this causes energy dissipation and tidal heating in the planet. And in kind of an equilibrium tide model, which is sort of the simplest tide model that we can have, this tidal heating in the planet is given by an expression something like this that depends on the eccentricity of the orbit as well as the obliquity or axial tilt of the planet. So this plot on the bottom shows this tidal luminosity as a function of the tidal quality factor, which is a measure of how dissipative the planet itself is, as well as the semi-major axis of the orbit. And so for just some kind of fiducial planet, mass and radius. So these contours here are showing the ratio of the tidal luminosity with respect to the incident stellar power. And so you can see that for pretty close in orbits, this ratio can be in excess of like 1%. So the tidal luminosity can be about 1% of the incident stellar power, which is a fairly significant extra effect on the planet. So this plot, I just used fixed values of the eccentricity and obliquity, but to talk more about the origin and independence of the eccentricity and obliquity components, it's kind of helpful to look at this in a little bit broader context. And to do that, I kind of like to talk about one of the best examples of tidal heating that we have in our own solar system, and this is Io, which is the innermost Galilean moon around Jupiter. And Io is the most geologically active body in our solar system because of the immense amount of tidal heating that it experiences. So Io has really, really strong tidal heating because it's locked in a resonance with neighboring moons that keep it fixed at a non-zero eccentricity. And this non-zero eccentricity means that there are continual changes in the strength and the direction of the tidal force exerted on Io from Jupiter. And so this sort of stretches and squishes Io's interior and leads to a lot of interior heat deposition. In addition to eccentricity tides, we can have what are called obliquity tides, so imagine now that Io's orbit was circular, but that it had a non-zero axial tilt. So its spin axis was tilted off of its orbital axis. In this case, the tidal bulge is sort of shifting with respect to Io's equator every orbit. And this leads to similar stresses and strains in its interior and leads to, can also lead to tidal heating. So both these components, eccentricities and obliquities, are important for tidal heating. And here's a look at this in 2 dimensions where I'm just plotting the normalized tidal luminosity as a function of obliquity and eccentricity. And I mentioned earlier that these Kepler multi-planet systems generally have fairly low eccentricities. And so in this regime, where eccentricities are small, obliquity tides can have a fairly several orders of magnitude stronger effect than eccentricity tides if we do account for this non-zero planetary obliquity. But however, these obliquities have kind of been largely ignored in the field of exoplanets thus far, to some degree, not entirely ignored, but largely. And this is because we kind of just assumed that they would be forced to have non-zero, forced to have zero or aligned values with their orbital axes. But in this talk, I'm going to give some reasons for why we think that obliquities of these close-in planets are actually important. And so I'll be focusing on the role of non-zero obliquities. So for the remainder of the talk, I'm going to propose that tidal interactions and particularly obliquity tides could naturally explain several of these architectural anomalies that we see in the short period planet population. And I'm going to discuss 3 specific examples. Okay, so the first topic I want to focus on are these so-called ultra-short period planets. And I briefly alluded to these earlier on when I was kind of giving some examples of architectural anomalies. But so the primary question that I want to talk about here is why we see planets with really extreme proximity to their host stars. These extremely close-in planets are particularly peculiar when we think about that planets form in disks, and so they shouldn't be able to form inside the inner edges of their disks. And these inner edges are thought to be controlled by magnetic truncation and roughly inside about a 1-day orbital period. However, we do see planets inside of 1-day orbital periods, sometimes as close to their stars as just a few stellar radii. And this population inside of 1-day orbital period are called the ultra short period planets, or the USPs, as I will call them in this talk. And it's generally agreed that these USPs can't have formed where they're currently found. For this reason that I mentioned above. And so they must have formed further out and then migrated inwards somehow. And so the question is, how did that migration happen? So in trying to solve this, we can kind of put together some of the observational clues. So one thing is that these USPs are pretty rare. They only occur around about 0.5% to 1% of sun-like stars. They're also a little bit more common around smaller mass stars compared to larger stellar masses. And their occurrence rate goes down with the orbital period, as you can see in this occurrence rate plot to the left. And finally, they're almost always pretty small planets, so smaller than about 2 Earth radii. And their compositions are consistent with being fairly rocky Earth-like compositions. So this suggests that if the planets were born with any amount of kind of atmospheric envelope in hydrogen and helium, then they likely lost those envelopes due to the immense amount of stellar irradiation that they're receiving on their short period orbits. So this plot shows all or almost all USPs in multi-transiting systems, and we notice that these USPs in red frequently have multiple close-in co-transiting companions. And statistical arguments have shown that they almost always have companion planets with periods less than about 50 days, even if they're not always co-transiting. So we also notice another really key feature of this distribution, and that the USPs tend to have larger period ratios with respect to their nearest neighbors that are generally a lot larger than the typical period ratios we see among these close-in planets. And so this is a suggestion that these planets could have started at the inner edges of such a system with a more typical separation with respect to their neighbor, before then kind of moving inwards. So these observational properties, specifically regarding that larger separation with respect to their nearest neighbors, points towards a formation channel via orbital decay driven by tidal dissipation. And as I was discussing earlier, one way that tides from the star raised in the planet can lead to dissipation in the planet is if it has a non-zero axial tilt. And one way to maintain a non-zero axial tilt is if the planet is in a configuration called a Cassini state, which I will describe in some detail soon. Okay, so here I want to describe this new theory for the production of these ultra short period planets from the innermost edges of a typical close-in multi-planet system. And I've named this Obliquity-Driven Tidal Runaway. And the process can be described in 3 component steps that I'll describe in more detail. And the first is entry of the planets into these Cassini states with non-zero obliquities. So to illustrate how this works, consider having just a 2-planet system with a bit of a mutual inclination between them that I'm kind of exaggerating a little bit here. But we want to understand how the obliquities of the planets evolve in this setup. So due to secular or kind of long-term average interactions between the 2 planetary orbits, both of the orbits are precessing around around the total angular momentum vector. So these purple and green vectors are indicating the precession around this black vector here. And the frequency of this precession we can call G, and it is in a low eccentricity and low inclination regime. It's just related to the masses and semi-major axes of the two planets. In addition, to this precession, there is also a precession due to the torque from the star raised on the oblate figures of the planets that causes their spin axes to precess around their respective orbit normals. So this spin axis precession is occurring at a frequency which we can call alpha. And the comparison of these two frequencies is critical for dictating the resulting dynamical evolution of the obliquity. So in this kind of precessing orbit frame of a planet, Cassini states are the equilibrium positions of the spin vector in that precessing orbit frame. So basically, if you're in this rotating frame, they are the positions where the spin vector is fixed. So this ds dt is equaling 0. And this condition can be written as this sort of simple expression here, where G and alpha are those frequencies of orbital precession and spin precession I defined earlier. Epsilon is the obliquity and I is the inclination. So there are up to 4 different Cassini equilibrium states that satisfy this criterion, depending on the ratio G over alpha, so the ratio of the orbital precession to the spin axis precession frequencies. I'm depicting these different states here, showing their obliquities as a function of this ratio. But the key thing is that in the presence of tides, only states 1 and 2 can be stable. And so on the right panel here, I'm depicting these different states for different values of the inclination, just to show how they depend on the inclination of the orbit. So the key idea surrounding this whole thing is that for close-in planets, tidal dissipation will force the obliquity to equilibrate in either state 1 or state 2. So if this ratio G over alpha is out here kind of beyond unity, then state 2 is the only state that the planet can occupy, which forces the obliquity to be at least the inclination or greater than that. And once the obliquity is forced to this non-zero value, that causes dissipation in the planet, which leads to orbital decay. And orbital decay tends to decrease this ratio G over alpha, which then increases the obliquity and leads to even more orbital decay. So this is sort of a runaway process. So just to reiterate, the key idea here is that the tidally relaxed positions of the obliquity or the Cassini states are non-zero values, and this makes sustained obliquity-driven tidal dissipation inevitable in these regimes. So as I've already alluded to then, once the obliquity is in this non-zero state, tidal dissipation leads to orbital decay. And the rate of this orbital decay induced by tidal dissipation can be calculated in the equilibrium tides framework, which I'm showing this timescale tau alpha, so the timescale of orbital decay, as a function of the orbital period of the planet and its obliquity for different values of the eccentricities shown with these different lines. So here's like kind of the 1 billion year timescale. And the key point to take away is that if a planet begins with a small enough initial orbital period and an enhanced obliquity, then it will decay to shorter periods where the rate of decay is even faster. And so this thus begins kind of a runaway orbital decay process. So for this last part, this process wouldn't work if this orbital decay just continues runaway indefinitely, because then the USPs would crash into their star, and so we wouldn't see them today. So something has to stall this orbital decay, and this is Cassini state breaking. So Cassini state breaking is essentially the limit at which the tides get too strong to maintain a really high obliquity. So as the orbit decays and moves up this Cassini state 2 branch, eventually the obliquity gets too large to be stable, and it breaks out of the state 2 and goes back down to state 1, which is a much smaller but still non-zero obliquity. So on the right here, I'm showing a couple examples of this runaway orbital decay, where the color bar is the obliquity. So I'm showing this for kind of different initial conditions. So the decay, you can see, goes runaway at some rate at which the orbital decay becomes really fast and eventually gets to a really high obliquity that breaks out of this state and settles down onto a much smaller obliquity that stalls its orbital decay at ultra short orbital periods. So because this kind of happens so fast, it's pretty unlikely to see this process in real time. But there is one example of a system that we think might be currently undergoing this runaway decay, which I could talk about later on if you're interested. So we've just kind of outlined this mechanism by which a short period planet at the inner edge of a multiple planet system can become a USP. But what is the region of planetary parameter space that is susceptible to producing a USP? And I don't have time to go into the details of how to derive this exactly, but as a function of the planetary mass and the initial semi-major axis, these shaded regions are sort of showing where a planet is susceptible to becoming a USP through this mechanism. And these regions are reasonably achieved for the inner planets of these short period multi-planet systems. If we compare these parameter space regions for different stellar masses, we can see that there is more space or more kind of support for producing a USP when the stellar mass is small. And so this is sort of in the same direction as the observational trend that has indicated that USPs are more common around smaller mass stars. So as far as kind of testing this theory of USP production with further observations, there are a couple of things that we can do. One thing is that we really want to obtain some better constraints on the eccentricities of the companion planets to USPs, because this could help rule out eccentricity tides as the cause of the inward orbital migration, and help give more support to the idea that obliquity tides might have played an important role. Second, I didn't have time to talk about this in detail, but another prediction of our work is that USPs should end up on orbits that are fairly aligned with the stellar spin axis, compared to their companions, which we think should be a little bit misaligned with the star. And so these stellar obliquities actually are observable, and we think that follow-up observations of these could help check this hypothesis. Okay, so kind of moving on to the next topic, which I won't discuss quite as in much detail as the last one. Just as this ultra short period planet problem sort of stems from some anomalies in the distribution of orbital periods, there are also some peculiarities that we can see when we look at the distribution of orbital period ratios of pairs of planets in the same system. So this problem, again, concerns the period ratio distribution, which I'm showing here for Kepler planets, just pairs of planets within the same Kepler multi-planet system. And so this x-axis is the ratio of just two pairs of planets, the outer period to the inner planet, across many different systems. And a feature that has been noticed as statistically significant here for some time now is that there is a bit of an excess of systems with period ratios just wide of the 3:2 and the 2:1 mean motion resonances, or these which are these integer period ratio relationships of pairs of planets. So it's a little bit hard to see here, but if we zoom in near 2:1 ratio, we can see that there's an excess of systems wide of that in a deficit inside of this. So these mean motion resonances, these integer period ratio relationships, or which I'll call these MMRs, these are naturally produced through convergent migration of planets when they're still embedded in the protoplanetary disk. So basically, planet disk torts lead to orbital migration in the disk. And if this migration proceeds in a convergent direction between two planet orbits, as I'm kind of illustrating with this example to the right, then if they encounter this like a 3:2 resonance, 1.5 period ratio, then they kind of get locked at that period ratio, even if the migration continues even further. So several authors showed that if the planets get captured into mean motion resonances through this convergent migration in the disk, and then subsequently, over gigayear timescales, they undergo tidal evolution due to tides raised on the planets from their host stars, then that could cause systems to move to period ratios wide of the exact resonances, kind of in this direction of the pileup that we see. But there's a caveat with this and a bit of an issue, and that is that these authors have shown that there would have to be a significant source of extra dissipation. So in other words, the planets would have to be a lot more efficient at dissipating tides than it's thought that they likely should be. So we're kind of in need of some extra source of dissipation that is a couple of orders of magnitude effect. And so based on kind of what I talked about in the first half of the talk, you can maybe hypothesize what I'm going to propose for this source of extra dissipation. So in the study from last year, we showed that if we account for the extra orders of magnitude of dissipation from obliquity tides, then that can be the sufficient kind of deficit to account for the deficit that we need to move planets wide of the exact period ratios by the amount that we see. However, this solution requires that these planets frequently have non-negligible axial tilts. And so what is there to suggest that they actually might have that? So it's not that we just think that these planets can have high obliquities, but that we actually fully expect them to due to a dynamical effect called a secular spin orbit resonance. So the key idea here is in realizing that these high obliquity Cassini states can be generated in two different ways. So the first was kind of this tidal evolution where orbital decay generates this large obliquity over time, as I was showing in the first half of the talk. But a second way is simply if this G over alpha ratio of the orbital precession to the spin precession evolves through means other than orbital decay, such as other evolutionary factors that are going on early on in the system's lifetime. And we call this mechanism resonant excitation because these G and alpha frequencies are evolving and becoming commensurable, meaning they're kind of crossing through this ratio of unity. So this is called a secular spin orbit resonance, and it's basically just another way of phrasing that it's a Cassini state. And this mechanism isn't new. It's actually what is thought to have generated Saturn's 27-degree obliquity. That this 27-degree obliquity is thought to be due to a secular spin orbit resonance due to Neptune-induced orbital precession G becoming resonant with Saturn's spin axis precession frequency alpha. So just to reiterate again, if the planet starts out here with the ratio G over alpha kind of in this regime, and this ratio evolves, then the planet obliquity can also get excited to non-negligible values. So in this work from last year, we showed that these close-in Kepler planets are actually highly susceptible to these resonances because of a just a coincidental frequency commensurability. That is that their typical orbital precession frequencies in the system, which I'm showing with this blue solid histogram, tend to have really similar values to the spin axis precession frequencies of the individual planets that I'm showing with these dashed histograms. So this indicates that as these systems are evolving early on and these frequencies are changing and becoming commensurable, then these systems can evolve into these secular spin orbit resonant encounters that pump the planet obliquities. And so we think that high obliquities should be a frequent occurrence and should be important for these close-in planets. So this has kind of been a qualitative description of this topic so far. So to give you a better sense of how this works and how these planets get captured into these high obliquity states, I wanted to show you like an example spin orbit evolution simulation showing what happens to a typical young planetary system as it is evolving and encountering this resonance. So the key idea here is that, so I'm going to start with just a star and 2 planets with all bodies endowed with structure, meaning that I'm going to account for the spin evolution of the planets in addition to just their point mass gravitational effects. So the key idea is that in order to encounter the mean motion resonances in the first place, as I stated earlier, they need to have encountered some amount of orbital migration. So again, I'm just showing kind of simulations here in which a migration rate of the planets is imposed to be starting slightly wide of a 3:2 mean motion resonance and moving inwards. And as I stated, I'm going to account for the tidal evolution of the planets as well as their spin evolution. So here is a result of kind of one of these spin orbit simulations. And there's a lot going on here, so I'm going to try to break this down. So the top plot are showing the obliquities as a function of time, and the bottom is the precession periods, which is just 2 pi over the precession frequencies. So if we look at these bottom curves, the blue and the green are showing the periods of the spin axis precession of the inner planet and the outer planet. And the purple is showing the period of the orbital precession. And so you can see that the inner planet, due to this, just the natural evolution of these frequencies that's happening early on, this inner planet first encounters this resonance where its spin precession period becomes equal with its orbital precession period. And this kind of causes a resonant kick of the obliquity. But because of some of the details in these dynamics, this resonance can only be captured from the other direction. And so when the planet again encounters this resonance from above, this forces the obliquity to this large, around 50-degree value, and which stops evolving when the frequencies stop changing. And so this planet ends up on this 50-degree axial tilt that it will just maintain indefinitely because it's locked into this resonance. And so it can be just dissipating with this high obliquity for an indefinite time period. So that example simulation is just demonstrating what we expect to be happening for at least some subset of these systems near these mean motion resonance pileups to create the degree of pileups that we see. However, there are some kind of additional interesting layers to this, and this comes about because some of the details that happen near these mean motion resonances, our hypothesis predicts that planets wide of these resonances should have larger obliquities on average compared to those just inside. And so if these planets wide of resonances are experiencing much more tidal dissipation due to their larger obliquities, then we should expect that increased interior heat deposition could puff up their hydrogen-helium envelopes and lead to some amount of radius inflation. So we would expect to see slightly larger radii for the planets wide of these resonances compared to those inside. So this actually brings me to the third and final kind of topic I want to discuss. And this basically follows from this line of reasoning to examine how planets might be having larger radii than we might expect due to the effects of tidal heating in their interiors. So I'm kind of moving away from the effects of tides on orbits to thinking about how tides affect the structure of the planet. So first, I just want to kind of follow that line of reasoning from before to examine what happens to planets wide of mean motion, to examine whether these planets wide of mean motion resonances do indeed have larger radii compared to just those inside or at other parts of the distribution. So to do this, I'm going to look at how the planet radii compare across the entire period ratio distribution. So this is just the period ratio distribution where I'm just binning it into bins of width 0.05. And then I want to look at adjacent bins in the distribution. So here are just 2 randomly selected adjacent bins. And then I'm going to calculate the mean planet radius in a given period ratio bin and compare it to the mean planet radius in a bin just prior to it. So here's just a mathematical representation of what I just said. And then I want to just compare that across this entire period ratio distribution. So here is the result of that calculation, where on the y-axis is the ratio of the mean planet radii across a given period ratio bin, plotted as a function of the period ratio. And the purple circles here are just indicating all spots where this ratio is greater than 2 sigma enhanced over unity. And you can see that the only places that this happens at are at the 3:2 and the 2:1 mean motion resonances. Although you can also see some enhancements perhaps at these other first order mean motion resonances. So the takeaway, at least is somewhat provocative idea here, is that planets wide of mean motion resonances seem to have a bit anomalously large radii compared to other planets in this distribution. So with this observation of these larger average radii for planets wide of these mean motion resonances that we expect to have large dissipation from obliquity tides, we can examine the question of whether this obliquity tide hypothesis offers a consistent explanation for these observations. So to address this, I built onto a sub-Neptune evolutionary planet model that was developed by Chen and Rogers 2016. And the model consists of just a spherically symmetric planet with a heavy element core and a gaseous envelope dominated by hydrogen and helium. And the envelope is evolved using the MESA stellar evolution code. So this code is built off of the MESA code that is typically used to model stars, but with some adjustments to account for the fact that this is a planet rather than a star. And so the only modification that I made to this model was just to account for the extra interior heating that we would expect due to the tidal heating that is that we are thinking might be happening. So to get a sense of how much these obliquity tides affect the planet radius of these planets, we ran a large suite of planet models within this kind of Monte Carlo over different key parameters, such as the planet mass, the amount of mass in the hydrogen and helium envelope, the strength of the incident stellar radiation, and then the strength of the tidal heating. Okay, so with all that set up then, the kind of main result here was to quantify how much tides affect the radius of these planets. So on the y-axis, I'm plotting the degree of radius inflation. So the radius that we get when we include tidal heating in the model of the planet compared to the radius that we get if we just ignore tidal heating. And I'm plotting this for as a function of the ratio of the tidal luminosity with respect to the incident stellar luminosity. So it's pretty clear that tides can pretty substantially inflate planet radii when this ratio is greater than about 10 to the -5 or so. And beyond this ratio, or beyond this amount of tidal heating, the planet radii can inflate by up to about 2 times their size in the most extreme cases. So very broadly speaking then, these simulations are plausibly consistent with this observational result that radius inflation of the magnitude that we see of about maybe 1.5 to 2 times their planet size could plausibly result from tidal heating based on the degree that we see in the simulations. But I think definitely more work would be necessary to confirm whether this indeed is a signature of tidal heating in these planets. But just given the last couple of minutes, we've seen that tides can pretty substantially affect the radius of these planets. And so we might wonder whether tidal effects could be seen in other aspects of the radii of short period planets. And so this brings me to a separate group of planets that I just want to touch on very briefly that we think that have been inflated due to tides. And this is a subset of these really low density sub-Saturn sized planets. So planets in the range of about 4 to 8 Earth radii that previous works have determined that it looks like there's about 50% of the mass in the core of the planet and about 50% in the envelope of the planet. And there are about roughly 10 to 15 or so planets that have been discovered with these specific properties. So planets like this, though, pose a challenge to core accretion theory because, and this theory represents the dominant paradigm of planet formation for gas-rich planets. And so this theory holds that if a solid core forms while the protoplanetary disk is still around, then it will accrete gas from the nebula at a rate that's set by its internal cooling. And when the mass of the envelope of the planet equals about roughly the mass in the core, then it will hydrodynamically collapse under its self-gravity and undergo a phase of runaway gas accretion that transforms the planet into a gas giant. So this theory predicts that we shouldn't see many planets with this kind of 50% core and 50% envelope because those planets should have undergone runaway accretion pretty rapidly. So the fact that we seem to have found planets at this kind of right at this threshold of runaway has been a bit problematic. So we have proposed a solution that maybe most of these sub-Saturns are not quite as gas rich as their masses and radii have suggested, but rather their envelopes just look big because they've been inflated through this tidal heating, mainly from eccentricity tides, but potentially also from some obliquity tides. So to just illustrate this with one example, we looked at this planet K2-19b, which is has a period of about 8 days and an eccentricity measured through rate of velocity of about 0.2. And when we use just standard core envelope structural models that ignore tidal heating, we can infer envelope mass fraction of about 40 to 50%, which is again really precariously close to this 50% runaway threshold. But if we include tidal heating in our model, then we get these posterior parameter distributions in the tidal quality factor of the planet and the envelope mass fraction. So this is how strong of dissipation the planet is experiencing. And so here we're just assuming that the eccentricity is fixed to this 0.2 observation, but we're plotting it for different values of the obliquity of the planet. So basically, the planet seems much less envelope rich than it initially seemed when we didn't account for tidal heating in the model. And basically what is happening is that this tidal heating is puffing up the atmosphere and accounting for some amount of the large radius that we see, such that we need less envelope mass to get a given planet radius. And the stronger dissipation in the planet, the less envelope mass that we need. So I'm running out of time, but we looked at this for just the whole sub-Saturn population with well-measured densities, and we found that many planets in this regime can have been strongly affected by tides in the sense that when we derive their envelope mass fractions without tides and with including tides, we see pretty large differences in those two derived estimates. And so many of these planets that were previously close to this threshold of runaway seem to have much more modest envelopes when we account for tides. And a big kind of takeaway from this also was that many of these sub-Saturns might just simply be sub-Neptunes that have been inflated rather than a separate group of planets. Okay, so just wrapping up now in these last couple of minutes, I want to just talk about how we could test some of these theories. And as far as obliquity tides, the most obvious and cool thing to do would be to try to observe a planet obliquity directly. And as I mentioned in the beginning, this is still really challenging, but there are some techniques that should prove fruitful going forward. And I think one of the most promising techniques for James Webb might be trying to measure deviations of the transit light curve from what you would expect from a spherical planet. So detecting the planetary obliteness, and that signal is dependent on the obliquity of the planet. And so we might get some residuals with respect to a spherical transit model that looks something like this, and these are dependent on the obliquity. And so I think this is a promising thing to try. Another proposed technique for measuring the planet obliquity is what's called secondary eclipse mapping, which is looking at the occultation of the planet behind the star and looking at creating brightness maps from the shape of that occultation as it passes behind the star. And this has been proposed as a technique for James Webb as well. And finally, for directly imaged planets, spectroscopic and astrometric constraints have been proposed to constrain the obliquities of these planets, but these are much more distant and kind of in a different regime than these short period planets that I'm talking about here. But so in short, there kind of are some promising methods for obtaining more direct constraints in the future, which would be really interesting as a test of some of these theories that we think that short period planets may frequently have non-zero obliquities. So just to sum up here, these close-in planetary systems are full of really interesting structure, but also some kind of interesting anomalies. And the dynamics of tides and perhaps obliquity tides could explain several of these features, such as the effects of ultra-short period planets and pileups wide of resonance, but also affecting the physical properties of the planets through tidal radius inflation. So going forward, I think that it should be interesting to keep examining these architectural anomalies and just overall better understand the role of dynamics and tides in affecting the features that we see. So thanks so much for your attention, and I'll take any questions that you might have.
All right, thank you so much, Sarah. Clap for everyone. Yeah, that was a very interesting talk and perfect timing. So we have some time for questions. So please raise your hands and I'll call on you as they go up. So Sam was first.
All right, Sarah, thanks so much for this great talk. I have tons of questions, but for the sake of time, I'll try to limit this to only a couple. So my first question is, have you considered like how this would affect hot Jupiters? And if like the tidal quality factors are just much, or such that the effects are much weaker for those systems? And then my other question was, could stellar evolution trigger this sort of the USP production, for example?
Yeah, those are both really great questions. And as far as hot Jupiters, if you're talking about or thinking about obliquity tides, so this is a paper that actually Josh Wynn and Matt Holman wrote back in 2005 about maybe obliquity tides could be the source of the inflated radii of hot Jupiters. But there's a problem with that idea because an isolated planet, as hot Jupiters we think often are fairly isolated in the sense that they don't have close companions. An isolated planet, it's difficult to maintain a non-zero obliquity. You can only maintain it if you have that orbital precession due to interactions with nearby planets. So probably hasn't affected too many hot Jupiters unless they have close-in companions that we don't see frequently. As far as stellar evolution, that's a really interesting question as well. And the answer is no, I haven't thought much about what that might do to USPs or if that could help trigger the mechanism, but you've got me curious to think more about that.
Yeah, if I could just quickly add, I think the tidal interactions go as like the radius of the star to like the 8th power or something like that. So I think it's a pretty strong effect if it does come into the calculation. And one other quick thing I did want to mention is that in terms of measuring obliquities, you can actually use astroseismology where you have a really long baseline to actually measure the stellar obliquity. So in transiting systems, that can give you a measurement of the obliquity of the planet as well.
Yeah, I definitely think that's a fascinating technique, especially for measuring obliquities for systems that are not as amenable to like Rossiter McLaughlin because they're smaller planets or something. So I would definitely really like to see stellar obliquity measurements of USP systems that might not be able to be looked at with RM. So yeah, thanks for mentioning that too.
Yeah, thanks.
All right, thanks, Sam. Do we have other questions from the room? While you continue thinking, I also have a question about the USPs. I'm not sure that I totally understand the story about the braking mechanism, but I was wondering sort of either, are there enough constraints from the theory that you can make predictions for the occurrence rate or like the detection rate of the USPs? And if not, like, can it be turned around, and assuming that that is the mechanism, you know, the fact that you alluded to the fact that perhaps there's one in the midst of its runaway decay, can you make a prediction, or could you use that to constrain the parameters of your theory?
Yeah, I think that if we did a sort of population synthesis sort of approach where we set up a bunch of systems, like run the dynamics and see how many of them become ultra short period planets with varying things like the tidal queue of the planets and things like that, then that model could potentially give you the occurrence rate, which we could compare to observations. We didn't do that in this paper just because there's so many different things that you would have to vary, like what the masses of the companions are and their initial separations, and so many things that made that hard. But I think that definitely is plausible, and that we would be able to learn a lot about like, I guess, like the tidal queues of the planets would be most interesting. I think I forgot the second question. Can you just trigger me?
No, I mean that was pretty much it. My question was whether you can predict what the occurrence rate of decaying orbits would be versus constraining the theory from it. Like, yeah, you've certainly answered that. And I guess I sort of a follow-up thought would be that I would expect that tests would be a good resource for building up the catalog of such planets. I don't know. I haven't been keeping up with whether or not people are doing that search these days.
Yeah, I've seen like maybe a couple USP discoveries in tests so far that are also in multi-planet systems. So it's tending to look fairly similar as what Kepler got. But I think, yeah, because the plot that I showed with all the ones in multis, it wasn't that many. There's only like 25 or so. So once we have maybe 50 to 100, it could be really useful for the statistics to understand. Maybe USPs show some kinds of trends with the types of multis that they orbit with, or some kinds of trends like that could help inform these theories.
All right, great, thank you. So I think we could take one more very quick question if anyone has last burning thought. Trevor has a last burning thought.
Not so much burning, but that was a great talk, Sarah. It's related to what you were just saying. Like, I was wondering if anybody had looked into the average size of USP companion planets. Like, are the average sizes of planets that are companions to USPs different like statistically from, you know, regular multis?
Yeah, I don't think people have done that, at least in the literature that I've seen thus far. I don't think anyone's looked at that, but yeah, I think that is a good way to test that, because we need like planet masses of the sufficiently large planet masses to do this. So I think that would be if we get large enough sample size, that would be a really interesting test.
Great. All right. So I think we're going to call it there. So thanks, Sarah, again. Everyone's clapping, but they're muted, so you can't hear them. Yeah, thanks again for visiting us today, and we hope to host you in person again sometime soon. And thank you, everyone, for being here for the talk.
Thanks so much, everyone, for coming and for your questions. Appreciate it.